So, kia kato katoa, and thanks for being here at lunchtime. So, I hope everyone is having break from work and enjoying the seminar today. Today, we're gonna have an amazing speaker and to talk about the John Hollings Award from last year NZSEE conference. So the project was on the building that you're probably familiar with if you've been in Wellington, the One Whitmore Street. It's by the waterfront, and it's well, I don't know, you can see the picture there, it's amazing, and it's a case study on architectural and structural integration, and it's probably it's considered actually an example of an A-grade office in Wellington. And today we're going to have Chris Pitt, director of Thornton, and Chris has more than 20 years of experience working on projects mixing up structural engineering and also architectural design, and in New Zealand and Australia. Chris has also it's also one of the winners of the Young Achiever of the Year award from the Property Council in New Zealand in 2016. So no more details from me. Chris, over to you, and looking forward to hearing more about the project.
Thanks for the introduction, Catalina. We're going to take some questions. This isn't a particularly long presentation. It's quite high level, but we'll take questions in the chat. So if anyone's got any questions along the way, I'll try and address them all in the chat at the end. And I think we're going till 1 o'clock. So as Catalina said, this presentation is a bit of a promotion for people to put in their entries for the John Hollings Award at the NZSEE conference this year. John Hollings was obviously an incredible engineer working in the seismic space in New Zealand, implemented some of the first use of capacity design techniques and things like that, particularly in the Wellington apartment space. We're very proud to obviously have been involved in winning this award with John's name on it. I think if you there's probably some information that Catalina and NZSEE have provided and will provide associated with this about applying for the award. How do I get my thing to go? This is kind of a bit of a site plan and kind of a plug from us, but we're Thornton. We're a specialist seismic structural engineering company structural engineering company based here in Wellington. We've been in Wellington since the late 1980s. And kind of got a heritage back till kind of Chris Dunning and Adam Thornton started the company way back. This kind of indicates a number of the projects that we've carried out recently, and some of them a bit longer ago. In particular, One Whitmore Street, as noted there, is kind of at the northern section of the Wellington waterfront. Just behind Jervois Quay. It's in the reclamation area of Wellington, which kind of extends all the way back to Lambton Quay. So it's in one of the kind of more the deeper sections of that, and it's kind of part of a group of buildings that we've been able to work on probably since Christchurch of base isolated office buildings. So those include One Whitmore Street, the Site 10 PwC building, which is across the road from us, the Site 9 Bell Gully building, which is also across the road from us here, and 20 Custom House Quay, which is a similar building to the one where we're looking at today, and that's where we've got our offices in the ground floor. As you can possibly see here or indicate here, we're relatively close to the Wellington Fault. It's kind of, you can see that dividing line diagonally running across the image there at the bottom of Tinakori Hill, which is the section of large section of bush in there. So we're quite close to the Wellington Fault, about 1.5 kilometres away. So this project was instigated by our client Newcrest, who's a developer based in Auckland, but recently they've done a lot of their work down here in Wellington. It was the second project we've done with them of this kind of scale down here, the first being the building we're in now, which is 20 Custom House Quay. It was kind of a hybrid kind of design build model, I suppose, where Newcrest had put together their own construction team consisting of some very experienced contractors and staff from a number of different Wellington construction firms that were engaged from early on to help us with kind of ECI and construction processes, programming and things like that from early in the design phase. The architect was Jasmax, services were 335, and fire was Enlightened Fire Solutions. And luckily, we also had a number of subcontractors involved in the project who were engaged early, who had been involved in the 20 Custom House Quay project. So they were MJH, Thermosash for facades, and Robinson Seismic for the base isolators. So as I said before, so where the site is quite an impressive site in Wellington, it gets a full city block. It's triangular, so not the most desired shape for a seismic structure, a resilient seismic structure. We always like rectangles and squares, but this kind of gave us the opportunity to try and achieve a kind of quite a regular system, perimeter type framing system around the building without needing to have kind of firewalls and things like that that would impact that. As you can see here, the waterfront is about 50 metres away across the road to the east, and the kind of thickness of reclamation in this area of the site is about 4.5 metres deep. And then below that, you've got kind of marine sediments, and below that is what's known as the Wellington alluvium, which is a relatively dense soil. And then below that, you've got rock at kind of somewhere between 70 to 100 metres or something like that in this area. So it's a complex site, as noted here, waterfront adjacent, deep soils, reclamation, liquefaction, and lateral spread risk. So there was potential for significant liquefaction in the reclamation fills, and also potential in the upper alluvium for some lenses of liquefaction. And because the substrate because the substrate is sloping, so the marine sediments, it's an old shoreline, and there's kind of a free edge in that the seawalls in Wellington were designed a long time ago and unlikely to meet the same levels of resilience as this building. We have the potential for lateral spread. That said, massive opportunities for this building. It's an incredible site, kind of panoramic views in all directions. You can see up to the beehive and see all of the waterfront. And so an amazing kind of like once in a lifetime site in Wellington. So when we've worked on a previous project before with the same client, so this was 20 Custom House Quay, and we were kind of looking for similar or the same kind of performance criteria as that building. So it's a importance level 2 building. So we're kind of designing for a ULS of 1 in 500 years. But that wasn't benchmarked against, it was benchmarked against current code, but we carried out geophysical testing, including shear wave testing down to rock, boreholes to rock, and shear wave testing, and established a more modern seismic hazard for the site using PSHA techniques, which were carried out by GNS. Being a base isolated building and having quite a long period, the results of that kind of were quite similar to, at the long period, the hazard and accelerations were quite similar to that of current code. And that's kind of what we've seen as being one of the benefits of base isolation, particularly in Wellington, is that you're not seeing this significant uplift in accelerations when you look at these PSHAs or the National Seismic Hazard Model. So we've gone for kind of 3Rs: resilience, robustness, and redundancy. So resilience, we've got a base isolation system, so that's providing an incredibly well understood performance. It's essentially an elastic or a rigid box on top of this isolation system. So it gives you a very good, predictable understanding of the deflections and displacements in the superstructure, so you can kind of provide a bit more a surety about what the performance of fit outs and firewall walls and all these sorts of components, the secondary components of a building, will how they'll be affected after an earthquake. High robustness. So there's robustness kind of built through the whole building, but in one part that I've talked about later is that we've used permanently cased piles as part of providing additional robustness to deal with some of these geotechnical risks, such as particularly the lateral spread. And some of that is to do with, just at the end of the day, we are provided with guidance from our geotechnical engineers about the likely lateral spread induced loads and displacements. But fundamentally, there's probably more risk and uncertainty in those areas than there is, say, in the superstructure. So the case piles provide like an extra significant increase in both strength and potential for ductility if required in a significant overload case. We also have the diagrid, which has significant redundancy. You can kind of take out, if required, if it was taken out by a tsunami, potentially, or a fire, you could remove significant portions of that diagrid structure without having a collapse. So in the ground, we looked at the base isolation structure. So we started at ground floor. So the ground level of the building is raised above the existing surrounding ground by about nearly a metre, and that provides the benefit of flood mitigation, and also simplifies some of the detailing required for the base isolation. So we generally try with these buildings to have the ground floor pass over the perimeter ground, and it just provides a much simpler and more affordable base isolation detailing. But we still needed to build a kind of a semi-basement below the building to accommodate the P-delta structure, so the large structure for the ground floor, and the base isolators and their support structure underneath. So we were still excavating down 2 to 3 meters into this reclamation material. So we weren't removing it all. We had a basement that didn't have cars in it. It was just a rattle space. What we tried to do to mitigate some of the risks around the ground and potentially these overload cases is that we wanted to have the largest we wanted to target having the largest moments in the piles within the depth of the casings so that we could have like a very high safety factor in effect over the loads that we were seeing from the geotechnical analysis. And what that meant was that we didn't want to have a fixed head pile because we wanted it to have the large bending moment to be in the casing depth. So we came up with a solution which was to have pin-headed piles that could transfer the load from the vertical loads and vertical loads from the base isolators down onto the piles. And the solution we came up with was these very heavy walled concrete filled steel tubes that would take the 1500 diameter cased pile and effectively reduce its size so that even under the axial force induced moments, the lever arm would be so small that it wouldn't induce large bending moments. And that also reduced the amount of pile head restraining structure and P delta structure that we needed in the basement. So these are a couple of photos showing those heads. So we transferred load into the concrete, even though it would have been probably transferred in without them, with a redundant load path of the shear studs. And the contractor came up with a clever way of perfectly leveling these things with a series of bottle jacks down in the pile cage. And that was quite a successful intervention without a huge amount of additional cost. And it saved a lot of complexity in the P delta structure above the piles. Above the piles, we had the raft slab. So you can see here on the bottom left, this is kind of the load transfer structure onto those pile heads. So we wrapped and provided soft compressive material over the piles to reduce the amount of load that be transferred to them with their rotation as horizontal building shears and lateral spread induced loads were applied to the piles. And then we built effectively a large raft slab over the top of it that was tapering in thickness depending on the actions required. So generally about 1,200 to 1,500 deep at the pile locations and thinning out to 600 deep in general. The building is base isolated. I went through my photos and couldn't find any better photos of it than this. But this is one of the base isolators for the building. We used LRB bearings. It was kind of, we looked at sliders, but the main drivers were we kind of had an approach that we were happy with from this previous project. We wanted to keep the displacements relatively small to limit because of the height of the building, the P delta structure can kind of run away on you if you start having very large displacements. And we knew that whilst we weren't going to have the kind of extremely low base shears that you can achieve with a pendulum, the downside of that is also there's potential for movement and wind. So it struck a good balance for this project using LRBs, and we didn't need that many of them. There's only 28 LRBs for this building on its 1,500 square meter footprint and 12 to 13 stories high. So 28 LRBs sitting over 28 piles. They were designed for 750 millimeters of movement in any direction, and testing was carried out in Malaysia, where they're fabricated by Robinson Seismic. In as you can see here, so as I said before, below the LRBs or the isolators is the raft slab. So that has to be designed to take the bending moments from P delta actions from the LRBs. So that's essentially you when they displace, you've got both a offset axial force, half of which has to be taken out at the base and half of which has to be taken out by the ground floor structure. And you've also got the shears being transferred across it as well, which have a vertical offset between where they're resisted by the raft slab and the centre line of the LRB. So the concrete raft slab deals with the P delta loads below, and in this case, we've had some success and improvement in speed of construction by using steel as the P delta structure at the ground floor level. The balancing of there's a requirement basically to not have too much rotation on your support structures with most isolators. So often the driving factor of that P delta structure, particularly if it's in steel at the ground floor, is around rotational stiffness. A few more photos of LRB installation. So because we have, you've got varying levels of tolerance as you build up the building. So we've got piles with their kind of 75 millimeter offset tolerance. Then we've got concrete and reinforcement, which has its own, and then we're getting into steel structure and LRBs above, which have got very tight tolerances. So in this job, we allowed drossbacks to be installed in the raft slab, and then they could allow I think M56 10.9 or 10.9 anchors to be installed in those, and that allowed about 30 millimeters of tolerance in any direction to allow the surveying of the LRBs. And then these were a couple of other things that we carried out on site just to make sure that we were getting some of these interfaces constructed appropriately. So the central one is casting of or placing of the effectively the dry pack, the grout underneath the isolator. So we did this about 3 or 4 times to make sure we were getting consistent results. But essentially, you have to pump grout underneath the isolator, and it's considerable size. It's 1,400 square. So it is one of the more complicated aspects of the construction of base isolation. And this is the other one just showing the filling of the drossback to make sure we were getting it fully grout around the whole of the anchor. Superstructure, so the building's a composite steel structure, so generally concrete filled steel tubes and for columns and the diagrid, and composite steel, generally cellular beams, secondary beams, and just beams with holes in them for the primary beams. The grid is about 12 meters from the internal columns to the exterior, and as you can see, it's a triangle. So there is no real specific grid. There's a whole lot of things that were set out by a number of different factors where the columns were positioned, but the kind of the longest span of the primary beams between the columns is about 9.5 meters. Composite construction, so com floor, Nelson studs fired on site, and generally it was a pretty repeated footprint of the building from level 1 up to level 12. The things that changed, as you can see here, there's a few unusual features. So you can kind of see these V-shaped steel sections which can connect out. So this is just something I like to do on these projects, is make sure that we're connecting the diagrid in with redundant load paths. So the diagrids are connected in always with steel back to the main steel, and then there's also reinforcing bars in the slab to tie it back in the slab depth as well. Yeah, and so with this building, with the diagrid, the whole idea with it is so it's a tall base isolated building, and it's because of the seismic hazard we have in Wellington. You either have to go for very large displacements to achieve lower base shear, or you have to accept that you're going to have slightly higher base shear in your base isolated building than what's probably ideal and what you see in other places where this is implemented with lower seismic hazard. Um, but the way basically you can get these tall buildings to work with the base isolation is that the diagrid acts like a box section. So effectively, it can transfer the overturning forces from one side of the building to the other, and in effect pick up the weight of one side to reduce any tension forces on the base isolators, and transferring shears around the whole of the building. So these are a few snips from the shop drawing model. Um, yeah, so relatively it it's a triangle, but it also has curves on it. So the curve on the north side and west side is kind of a 215-meter radius. So a relatively gentle radius, but it does mean that all of these nodes need to, none of them are kind of planar, so they've all got some oblique angle or complex angles to them that makes fabrication of them somewhat difficult. And this is kind of what's shown in the top right is one of the corner nodes. So we had at the skinnier ends of the building, we had some corner columns to limit the compression and some of the tension on the corner base isolators. But it's a very complicated piece of fabrication, and the steelworkers did an incredible job with some of this very complex steelwork. What's going down the bottom there is so the way that the columns are connected to the nodes is with captured nuts. So the nut is installed inside the tube and effectively can't be accessed. So there's a series of plates which hold those nuts in place, and we needed to work out effectively how much bearing area we needed at the end of the tube. So that red area that's indicated there is effectively cut out of the nut capture device to allow full and solid bearing of the concrete fill, which was a self-compacting concrete, and that was then topped up. They were all fully filled right at the top with no non-shrink grout. Construction and fabrication. So, as I said, very complicated nodes, but other than that, a very repeatable floor plate. So there's a lot of complexity in some areas, but a lot of simplicity and repetition elsewhere. The main floor plate, I mean, this is what the A-grade office you want. You want big open spaces, 12 meters from those internal columns to the diagrid. Cellular beams for simple routing of services. And in principle, that one of the things that we find on these projects is that the fabrication, particularly of the P delta structure at the base of the building, which is so heavy, has a very long lead time to get to site. So there's all you have to indent all of that steel, and then it takes a huge amount of time to weld up each of these nodes. And the ones at the ground floor are the largest. So they've got the biggest welds, something like 50 and 60 millimeter full pen butt welds all over the place, as you can kind of see here. So we're working really with the contractor and with the fabricator to do early shop drawing processing. We'll do early consenting and tendering for a number of these trades well in advance of the architectural building consent. The other thing to achieve these kind of tolerances, you're talking about parts of a degree, is that in general, these nodes end up having a number of their faces machined. So full face prep with kind of end mills, MJH for the twin custom house key building, purchased a 5-axis aeronautical milling machine, I think looked like it's from about the 70s, um, that they've repurposed and are using in their workshop, and that we've effectively oversized the end plates and allow a kind of a maximum depth of cut so that effectively those end plates end up being machined to zero tolerance, and so do all the ends of the tubes as well. A couple other things from construction on this job. So, with the three-level diagrid, the way that we've constructed them generally is you erect all the steelwork for 3 stories, and then we'll do the com floor and concrete slab on the 3rd floor first. So the com floor, the tray will be laid in on the 1st and 2nd floor, just in packets, and then the 3rd floor is decked out and concreted, and that allows the steelwork to start on the next jump whilst we're infilling concrete floors underneath. So it provides some uh, program advantages. On this job, also, just because there's a lot of work and a lot of big heavy bolts around the perimeter, the contractor elected to use jump screens, which was kind of an innovative approach that we don't see often in Wellington. See them more often in Australia with these kind of jump slabs. And that effectively was a screen that kind of cantilevered up about 3 stories and provided protection for wind and also dropping of any objects. So, as you've probably seen from the photos, this building is quite aspirational in terms of its architecture and obviously its structure. There's a lot of integrated design. So, um, the building is kind of a glazed skin with these white precast canopy fins at the bottom. That's kind of how it started. So we did a base build, and it had a very simple sloping base, a flat monopitch roof, and then everyone got very excited when the tenant came involved, and we designed a beautiful and extremely difficult to design complex roof. So there's actually a roof oculus, and an outdoor area in the center of the main roof up on the top. And there's also mezzanine floors up at the top level. So, as you can see in the top right-hand corner, very complicated geometry. It's kind of aligning with both the complex plan geometry of the building, but a lot of shape in the roof form. So really the only way this could be done in any kind of cost-effective and time-effective way was with full steel construction and prefabrication. So whilst there ends up being a timber battens and plywood over the top of the whole thing, the whole substrate was constructed in steel. Yeah, so from the perspective of the architecture, what we work through generally on these projects is you want to have a good combination of simplicity in the building and complexity. If you're just providing, if you've got a complex site and a complex design and you're coming up with complex solutions, that's a real opportunity for a lot of risk in the project. So, what we often do in the benefit of the diagrid is that it kind of has to be on the outside of the building. It kind of is what it is, and it provides a lot of leeway for had to have multiple teams, one kind of working on the seismic system from early on, and another working kind of on the standard floor plates, and then you can have someone working with the integration. So both the integration of the architecture and the services, of which there's a picture down the bottom right. So as with all modern office buildings, you've got a lot of services. This is only showing the mechanical air plant, the fan core units. Um, but for the floor to floor that we have designed the building for, we've got a very high ceiling height. So essentially, the service zone is squeezed. We've got to fit all our structure in it and all the services. So nearly all the services are coordinated and run through those cellular beam holes. Um, and that also then had to allow for both the changes that would inevitably come with a fit out. Um, the way we did this was we had the benefit of having done this before with some of the same consultants, but a lot of it came down to planning, doing things on drawings right from the onset, blue beam markups. We didn't go into 3D straight away. We worked out how we were going to do it first before we got into the 3D world, because what we've generally found is if you start modeling too early, you just spend all your time remodeling. And that made the coordination process actually very simple. Sustainability. So no one's saying this is the greenest building that's ever been built, but we spend a lot of time and a lot of effort on these buildings trying to make their impacts on the environment as low as possible, while still achieving all those project goals and keeping the risks for the project relatively low. Um, so the general approaches that we took on this project was trying to enhance the design life. So the foundations, for example, we've designed them for a 100-year design life. Most of the building is encapsulated within the envelope. There's only small parts of the building, for example, the basement, which are really exposed to exterior conditions. So most of the building is in a situation that essentially durability is can be managed for a very long period of time. Obviously, the base isolation system and the resilience of the building mean it's less likely to be demolished in the long term, which is just less buildings we have to build in the future and less material going to landfill. And we also looked at reduced carbon options. So generally, what we looked at with that was around, so we couldn't really compromise things like we needed to have high strength concrete fill in the steel tubes, which just inevitably does require a lot of cement, unfortunately. Um, but we looked at a number of things around, reviewing of the seismicity and where's best to target the base isolation system. Looking at things like live loads. Are we using the lowest live loads we need to for that are suitable for an office? Some A-grade office building gets designed for 4 and 5 kPa throughout. This building is designed for standard numbers, and really reviewing the SDL requirements. So kind of how much material above and beyond the live load will be put in and realistically be put in the building. And we often, because there's not generally a big impact of having a high SDL or higher SDL for gravity load design, we generally allow different SDLs for gravity and seismic. So it's almost like we're applying an area reduction factor on the SDL to better reflect in reality the more likely seismic mass of the building. Yeah, so interrogating performance. So another one that in particular can have a huge impact on carbon in buildings, particularly buildings of this type, is vibration requirements. So we really worked on that with the client. Clients are always very particularly don't want their building to be known as one that's has vibration issues, but really working through those processes and understanding what is the right level to be at, and where it can be optimized. This building is, from a typical building. This is a very light building. It's kind of I think 5.3, so about 550 kgs a square meter total seismic weight. Um, so it's a very light building as well. So we used Resitec, which is a elastomer product between the com floor and the steel beams to reduce the need for adding extra mass or adding extra stiffness to the steel beams. Um, Obviously, all of these strategies can come with a compromise on performance, so making sure that the client is bought into those decisions and understands the decisions they're making. But often it's kind of the third parties, like the tenants that have I wouldn't say onerous, but can have requirements in their BPSs that can often be don't provide a huge amount of value for the amount of carbon and general project cost of what they're getting. And I think that's an area that really probably should be targeted with some of these BPS conditions that are being put on buildings because it does actually really impact the ability to design and build lower carbon buildings. Um, Things like conservatism, we try and limit the conservatism, obviously, in the buildings. And I think particularly understanding a building type and having done it before gives you the opportunity to be um, not having to build in so much conservatism at the concept stage that often inevitably ends up sticking around till the building's been built. There's also, I've just put a link down here for a very good resource from iStruck out of the UK, which provides some really good information, like this diagram on how we can try and deal with climate crisis and structural engineering. Um, and then I've got a few beautiful pictures, but I think are coming to the end of my talk. Um, Yeah, so this is the mezzanine floor and oculus up at the roof level. So, just when you think you've designed all your diaphragms, you get one that's not connected into half the diagrids of the building. Um, but we made it work somehow. Yeah, and it's a beautiful space in the Wellington CBD. Great addition. And this is one of the main features of it that you can see from the ground floor is Lincoln Fraser, who was the main client's representative and the family who owns Newcrest. His father was involved in precast for a number of years, so we really wanted to look at using some precast on the project, and we've designed these post-tensioned white concrete. So there's no coatings on these white concrete fins that support the canopy and also the glazing. And an incredible job by the architect and the contractors to resolve all the complex detailing around this. And just again, another plug, just a plug for putting in your uh, entering for the John Hollings Awards. I think it's just some text that you need to provide at this stage, and then a poster for the NZSEE conference. I'd suggest. I wish that all of that text had been written by ChatGPT, but I think someone actually wrote it here. I don't think you need that much text. So it's not as daunting as it probably looks here. So it's certainly worth entering. It's always good to see the kind of projects that people are doing out there in this space in New Zealand.
Thank you
So,
very much, Chris.
well, good.
Yeah, that was great. Amazing project. Just want to add that the application closed next Friday on the 7th of March. So yeah, looking forward to see a lot of applications. And yeah, thank you once again. And you can see that we have a couple of questions.
So I'll go through these.
Okay, sweet.
Um, Thank you for. if the Yeah, so someone's asking, essentially, it's a relatively tall building. What's the point of base isolating it? Because your base shear will already be relatively low, with a because of how tall it is, it'll have a longer period. Um, Part of the issue in Wellington is that if so, you couldn't do a diagrid building probably like this. Without it being base isolated, it would be too stiff and the overturning forces would be quite large. So you end up basically with extremely high base shears. Going to a more conventional system, well, the question is, what is that conventional system? Do we even have, are there viable conventional systems that are even can be designed for these kinds of buildings for um, the kind of seismic requirements we have with these PSHAs and the National Seismic Hazard Model? I suggest the answer is for a building of this scale, no. You kind of have to look at base isolation or a viscous damped solution. Um, the reality is that these buildings are actually reasonably cost effective and low weight, and the amount of steel in them is actually not significantly high because of how efficient they work, because they spread the load so well around the building. A building of this height in Wellington, if it was, say, a concrete frame, would probably be about 2 second period. Um, this is kind of 3+ second period at the CALS event. Plus, you're getting 30% damping. So you're still getting a significant reduction in those loads with this kind of building. One of the other benefits is you're just getting you're getting a reduction in acceleration and superstructure drift. So that superstructure drift is a huge component of detailing and the requirements for facades and resilience and these if you really want to achieve high levels of resilience in a building, there's no point in having a structure that's fine, but you've destroyed all the finishes. So the drifts in these buildings are kind of in the 0.3% range in the superstructure. So typical detailing for a curtain wall, typical detailing for a jib wall, achieving that can achieve close to a no damage kind of outcome in a 1 in 500 year event. How does the lateral load path work for intermediate floors that are remote from the diagrid nodes? So it's a hybrid diagrid. So it's a diagrid and a moment frame. So the perimeter has effectively has there's 16, I think 16 or 530 UB. There's 530 UB perimeter beams that are detailed as a moment frame that can transfer the loads from the intermediate floors to the diagrid. There's been other approaches on other diagrid jobs, projects like having, a concrete core or something like that. This integrating a concrete core into a building like this is complicated, and this provides a reasonably simple load path. Um, nice one, Chris. Did you use or refer to the NZSEE isolation guidelines? Yes, so this building was followed the draft NZSE isolation guidelines, which was a great document to have because it was good to have something that was having a basis in the New Zealand codes. That said, still have a large number of comments on that draft guidelines, which can be talked about at another time. And how is fire resistance of the cellular beams provided? So the cell beams were fire rated with intermittent paint. The building's a 30-minute fire rated building because it has so much ventilation on the perimeter and the fire case. We used a product that could be applied to black steel, so it was very efficient. And then the concrete columns were obviously achieved their own fire rating of in excess of 1 hour fire rating. I think that was all the questions. Very much on time.
Yeah,
Thank you
I
very
think
much for
so.
your time.
Oh, thank you. And thank you everyone as well for coming to the seminar. Um, yeah, just to encourage everyone to apply and go to the website and you can see other projects that have been awarded the John Hollings Seismic Resilience in Practice Award. So yeah, thanks once again, Chris, and I think that's it.